but I actually published a paper. This is the first annual Artificial Intelligence Conference. Back in 1985, they decided that, hey, this AI thing looks kind of important. Let's start having an annual conference on it. So they asked me to write a paper, and I wrote something on Bayesian recognizers. It's kind of in depth, so although it's a good question, I'm going to kind of deflect it for now. And we'll get into that. The next time HBRC can't find a speaker and needs a spur-of-the-moment replacement.
In 1985, wasn't that the AI winter?
Well, there was a winter for neural networks. And most of that was because we didn't have the hardware. The concepts were there and developed, but it sort of waited until we had GPUs and high-end CPUs before neural networks sort of made a resurgence. So in that sense, they're not really new. They've been around for many, many decades. But now they're interesting.
85 was expert systems.
Expert systems? Yeah, I don't really know too much of the history off the top of my head. I'm getting older. So the next thing after Watson, I'm assuming I was talking, I wasn't paying attention. Did he flip over in the end?
Yeah.
Okay, good. Of course I knew he did, I've seen the video. The next one is I decided, let's do something a little more complicated. I want him to learn how to walk, rise up and walk. So now we're starting standing up. His IMU is in his chest. And the simple command is increase your delta distance in XY, but don't let your Z fall below half of what you started with. So in other words, move from your initial position, but don't fall down. And that's how I mathematically defined walk. And it's the same algorithm. He'll do something at random and he'll fall. And he'll do something at random again, but he'll fall a little bit slower if you noticed. And then eventually, here he goes. He took a step and he didn't fall, and he took a second step, and his third step he fell down. But he learned from that, so of course he's going to repeat what he knows works with slight variations, and then try to add to that to get a sequence of walking going. Question?
Yeah, I have a quick question. So, how do you enumerate like the commands to perform a motion? Is it like a number, like a string that says like move left leg, or how are you organizing that?
In this particular model, the commands are simply, he has 16 servos, and it's simply a vector of 16 numbers saying, go to that position. And that's it. And it's just a sequence of positions, keyframes of animation. And
he's guessing?
He starts off random, doing something at random, and as he finds a position where he's still standing, he's going to remember that. It's like the beads. We add 3 more colored beads to do this because you're still standing. And you can see, it doesn't really take hundreds of iterations to do this. I think he gets up to, 7 steps. And even though this video is showing this happening in about 2 minutes, 33 seconds, he actually learned how to take 7 steps in a row in about 8 milliseconds. Because when you're in the simulator and you're not having to render, things are going a lot faster. This is just so we can visually see what's going on.
How do you prevent getting bogged down in a local valley rather than finding the optimum solution, or even a viable solution? If you're just saying that the thing made progress, well, I'll randomize that. You might never get out of that valley of that solution in the search space.
That is a notorious problem in AI. There's a buzzword called hill climbing, and that is when you find yourself in a particular, test state, you're going to check the states around you to find which one's better, and then you're going to go in that direction in the search space. When did this stop?
Finished.
Oh, it finished. Okay, again, I was talking and not paying attention, but at the end, I think he took 7 steps and then finally fell over. What he does do is, even though he does 7 steps in a row, the next time he's going to do those 7 steps, followed by a trial of an 8th, he's going to slightly modify those 7 steps to see if he finds a slightly better version, and that's the hill climbing version of what a genetic algorithm is doing. There's a lot of art to crafting a fitness function and of crafting your mutation function. For example, you can completely randomize all 16 values to try that as a new test. Or you can say, you know, that last one kind of worked. I'm going to keep 14 of the values and I'm only going to randomize 2 of them. Or you might even say, I'm not even going to randomize them that much. I'm only going to nudge them by plus or minus 10. So there's an opportunity to sort of have a genetic algorithm on top of the genetic algorithm parameters of what you're really trying to learn, so that you can learn what's the best mutation function. So you can sort of recursively apply these things to themselves to get rid of that problem. And of course, if you have a population of 1,000, like in the bugs, I think I set the max number as 1 million. You want as much genetic diversity as possible. So if you do find yourself in a local minima, if your mutation function is enough to mutate you outside that valley and into another one, then you'll slowly converge on that new local minima as well. There was a great picture of a website that I saw this morning. I'm not going to try to find it. But basically what we're doing with AI, people always ask, what's the purpose of AI? And there's a million answers to that. There's one that I really like. Let me see if I can find it. No, that's not it. I didn't download it. But basically, as you noticed, we'll take the example of checkers. It's a huge problem. And trying to find the exact solution to checkers or any other given problem is huge, it's humongous. And some problems we just can't solve. So the purpose for me, or what the crux of AI is, regardless of which algorithm you use, its purpose is to reduce the solution space as much as you can so I can find a good enough local minima solution. So it makes problems that normally would be unsolvable. Now, it depends on what your definition of solvable is, but we get a pretty good solution. Great examples of that are like traveling salesmen. You have 1,000 cities and we want to find the best path. Everybody pretty much knows that one. There's lots of AI heuristics and algorithms to get a pretty good solution without having to explore the entire space. So if you can imagine the search space with hills and valleys, it reduces the search space to every state, to every hill. And that's a significantly smaller problem to search, because once you're within a local minima, you're going to hill climb, find what the peak of that valley is. So that's a really good question. That's what we want to do. So that was Watson learning how to walk, and bugs learning how to find grass. The cool demo is, everybody knows the tabletop challenge, and most people here know MockBot. Again, a simple Arduino-based computer. And actually 2 days ago, I decided, wouldn't it be cool to write a demo with MockBot to not know how to do the tabletop challenge, but for him to learn by himself how to do the tabletop challenge. So I wrote a really quick example. I'll really quickly throw up the code, just not to go through it, but just to show you the components that are in there. And this is just simple Arduino code that you guys can look at, take a copy, modify it, play with it. It's really fun stuff to get something like an Arduino Nano to actually learn. And old dual core computers, who wants access? Sure. Anyways, I'm not gonna wait. Oh, there we go. Is that readable?
Yeah.
Barely. I'm gonna highlight this to see if does that make it more readable?
No.
If I highlight it,
I
no.
think you can make the font bigger.
Yeah, you can change the preferences.
File preferences.
That is.
Oh, there we go. Font size. Let's double it, make it really big.
That's crazy.
Ah, there we go. Just go full screen on this. Now is it readable?
Yeah.